Welcome back to Maths with Mrs. J. I now wanted to talk with you about piecewise functions. We did introduce this concept in our previous video where we met the absolute value function. I wanted to go through that one again now and also talk about some other piecewise functions, how you would graph them, how you would recognize what they are from their graph, and also start to introduce the idea to you of continuity, discontinuity, limits, and that sort of thing. That's a whole other series of videos, but I want you to start thinking along those lines now. All right, if we have our absolute value function, basically it's the same as y equals x for any values of x 0 or above. So that's the line y equals x. For any values lower than 0, you get the function y equals negative x. So that's what your function is going to look like. How you draw a piecewise function basically is you draw the appropriate section of whatever graph it is for that particular x value. So if we're doing x less than 0, we want to draw the line y equals negative x, which looks like that. So that's the line y equals negative x, but we only draw it for values of x less than 0. For values of x greater than or equal to 0, we're drawing the line y equals x. That was y equals negative x, this is y equals x. How do I know that they actually touch at 0? Well, if you substitute in x equals 0 into both of these, you'll see that they are the same value. If they were a different value, then you will have a discontinuity or a jump in your graph. We'll see what that looks like in this example here. All right, obviously 2 is the sort of crucial x value here. So let's have a bit of a look at what's happening here. When x equals 2, the y value, or f of x, if you want to think about it in terms of function notation, is 6. So at x equals 2, the y value is 6. So we've just got a dot there. All right, it's only for that particular x value. All right, if we're taking the section of the graph from x is 2 and above, what we've got is the graph of y equals 10 minus x. Now that's going to be a line, straight line with a negative gradient that would have a y-intercept at 10, but we're not actually using that line there, that point there, because when x is 0, this function isn't in play, but that's where it would be. And your x-intercept is going to be at 10. What is your value? I know that x equals 2 is not included here, but let's see what the value would be. If x were 2 and you were to sub that in here, you would get 8, wouldn't you? What we're going to do is we're going to do an open point there to say that that's what it would be there. It's not actually defined when x is 2 for this particular function. However, we have an open point there, and we're going to draw a line between that and our x-intercept. So what we've got is this. If this were to, and let's actually continue that on, because it doesn't specify any particular top range of our domain. You will notice already that when x is 2, there's a jump in the graph. There is only one y value there because this doesn't count as a y value for x is 2. However, there is certainly a discontinuity in the graph there. Now let's have a look at the section of the graph where x is less than 2. This is your basic garden variety parabola. So we know that it's going to go through the origin. We know that when x is negative 1, y will be 1. When x is 1, y will be 1, that sort of thing. If we were to work out what the value of x squared is when x is 2, we would get 4, wouldn't we? So this curve is going to come around like this, up to, but not including the 0.24. This would be what this graph would look like in terms of our 3 individual piecewise rules. Now let's think about this. Is this a function? Well, it actually is, because at this, well, obviously everywhere else is perfectly fine, but the point that we need to be particularly careful of, at x equals 2, there is only one y value there. This is an open hole, this is an open hole. They are not the y values there. It approaches there, but doesn't actually equal that. So yes, it actually is a function. What is the domain? Well, the domain is actually all real numbers. What is the range? Well, also, we're going to have all real numbers. All right, that's an interesting one. So just again to explain how to graph a piecewise functional relation, you're basically drawing several graphs in one, but you're just drawing the appropriate sections according to the x values. All right, let's go on and have a look at some more. And let's just have a look here. Right, we're just going to do a few more examples where we don't have to do too much graphing because that's a little bit tedious and time consuming. We're going to have a look at some examples here. First of all, just working out, if you're given a piecewise function, how do you work out f of a particular x value? Which version, if you like, of the function do you use? Well, f of 2. This function, the sort of crucial point where the rule changes is x equals 0. When x is greater than 0, and 2 is certainly greater than 0, the value of the function is 2. So that's just going to be 2. F of -4. Well, -4 is less than 0, isn't it? That's an x value less than 0. So we're going to be taking this version of the rule for that. When x equals 0, well, which one of these rules includes x equals 0? It's this one. F of a half. Well, a half is greater than 0, isn't it? So the function will be 2. All right, let's looking at our g of x example. The crucial point here is around x equals 3. That's where the rule changes. So g of 7, 7 is definitely greater than 3, isn't it? So we're going to be using this bottom version of the rule here. So 2x minus 1. 2 times 7 minus 1 is 13. G of 0, well, 0 is less than 3. So we're going to be using this top rule. 0 plus 5 is 5. G of -1, well, -1 is also less than 3, so we're going to get -1 plus 5, which is 4. And G of 3, which one includes the 3? This top one includes the 3. 3 plus 5 is 8. Finally, our H examples. Here, the point to sort of be careful of is x is -2. -4 is less than -2, so we're going to use the top rule here. A half of -4 is -2, minus 4 is -6. -2, which one includes the -2? The top one does. So we're going to get -1 minus 4, which is -5. -1 is greater than -2, so we're going to use this version here. That will be 5. And 6, of course, is greater than -2, so we're going to use this version here, which will be 3 minus 12, which is -9. This is an interesting activity, this one here, trying to match up the piecewise functions with the graphs. Okay, all of these are just straight lines, all right? So it shouldn't be too difficult for you to work out. In particular, there are special cases of your straight lines. If you have something like f of x is -5, we know that that's just going to be a horizontal line down at y is -5. So these two here are going to be the two graphs where you've got a y equals -5 happening. So that should be able to help you to work out those two. This one is -5 when x is less than 1, and then a different function for greater than. So that has to be 17. This one is y is -5 when x is greater than 1. So this would be 18. So that's those two sorted. All right. Let's have a look at the other graphs. All right. Well, these ones have their, I guess, important point around x equals 0. So there are two graphs here where 0 is the important point. There's F and there's B. Let's have a look and see which one of these is going to be which. This one, when x is greater than or equal to 0, you're going to get a y value of 3. It's going to have to be this one, and when x is less than 0, you're going to get y equals x plus 4, so it would be coming in to a y value of 4. This one is going to be F, so that's that one, and this one will have to be B. The other two are where x equals 1 is the sort of crucial point. Just thinking about this here, it should be easy to work out which one is which. This is y equals 3 of x when x is greater than 1. So it should be at x is 3 there. Both of them are at x is 3 there, so we can't use that as a discriminating fact. Let's have a look at the y value for x less than 1. 1 minus 4 is -3. This one would have to be E, and this one would have to be D, and we're done. That's quite an interesting exercise, that one, to get you thinking about what's happening where. All of that was linear. There's nothing terribly difficult about it. What you need to do is think about what the crucial x value is in each case, and what's happening on either side. To the left when x is less than that value, and to the right when x is greater than that value, and which rule includes your x equals 1 or 0 or whatever the crucial value is.